Rotating square reflectors. Two square reflectors, each A is equal to 1.5 centimeters on a side and of mass m equals 4 grams, are located at the opposite ends of a thin, extremely light, D is equal to 1 meter rod that can rotate without friction and in vacuum about an axle perpendicular to it through its center. So it can rotate about this axis of rotation. So these two square plates can rotate. These reflectors are small enough to be treated as point masses in moment of inertia calculations. Both reflectors are illuminated on one face by a sinusoidal light wave having an electric field of amplitude E is equal to 1.25 newtons per coulombs that falls uniformly on both surfaces and always strikes them perpendicular to the plane of their surfaces. One reflector is covered with a perfectly absorbing coating and the other is covered with a perfectly reflective coating. What is the angular acceleration of this device? The area of each reflector area A is equal to side length A squared. So we can calculate the area as 1.5. It was 1.5 centimeter on the side, so 1.5 times 10 to minus 2 squared. The mass of each reflector is 4.00 grams, which is 4 times 10 to minus 3 kilograms. The maximum electric field that hits the surface perpendicularly with the sinusoidal electromagnetic wave is 1.25 newtons per coulombs. The average intensity of the light, which is the average time averaged value of the Poynting vector magnitude, is 1 over mu 0 time average value of E times B, electric field times the magnetic field, which is 1 over mu 0 because E is equal to B times C, time averaged value of E squared over C, because B is E over C. So this gives us, if I multiply the top and bottom with C, I will obtain C squared at the bottom, and C squared is 1 over mu 0 epsilon 0. So with that, I will obtain epsilon 0 times C E max squared divided by 2. Okay, so here I have noted C is 1 over mu 0 epsilon 0, the speed of light, square root. And the time averaged value of E squared is E max squared over 2, as we have shown in the lecture. Now, the average pressure exerted by this sinusoidal electromagnetic wave, P bar, is the force divided by the perpendicular area, and we are given that it's hitting the surface uniformly. So this is basically the force being exerted divided by the area, which is A squared, and that is equal to the average intensity divided by the speed of light c for complete absorption, as we have shown in detail in the previous problem, and this average pressure is equal to force divided by A squared, and that is twice the average intensity divided by the speed of light if we have full reflection. And remember that we have both of these types present. One type is on one square, the other coating is on the other square. And with that, we obtain two different forces here. So let's take this over here. Or let's take it down here. Because I'm going to write two different types of forces. The force that I will obtain from complete absorption scenario is F is equal to epsilon 0. Now I'm looking at this equation, I average divided by C, so that's going to be epsilon 0 E max squared over 2. Epsilon 0 E max squared over 2. That's the average intensity divided by C, and it's divided by area, so force is equal to I average over C multiplied by A squared. So I will have a factor of A squared here. For the case of full reflection, the force is equal to 1/2 of this value, epsilon 0 E max squared or twice this value, epsilon 0 E max squared A squared. You can see it's twice I average over C. So I average over C is epsilon 0 E max squared over 2. Multiplied by 2, we obtain epsilon 0 E max squared A squared. Now, what is the moment of inertia for this setup here? The moment of inertia I is sum over R square mi square, for I being the mass index for point masses. So Ri square mi square, where Ri is the distance with respect to the rotation axis. So in this case, I have the point masses here at a distance d over 2 from the rotation axis. So m d square over 4 for this one, and m d square over 4 for this one. So it's going to be twice m d square over 4. So it's 2 times m d square over 4, which is m d square over 2 for this rotation axis. What is the corresponding torque? Torque is equal to R cross F. So if I write the torque here, the force, one of the forces is epsilon 0 E max squared A squared. The perpendicular distance is d over 2. So if these electromagnetic waves are hitting these two surfaces at the same time from this direction, the force R cross F, there will be a torque in this direction, R cross F. So R cross F, there will be a torque in this direction. So these torques are opposing each other. Using the right hand rule, if I look at this perpendicular force here, four fingers of the right hand point from the rotation axis to the point of application of the force, and we curl them towards the force. So R cross F gives us a torque vector into the page, implying clockwise rotation, and this is implying counterclockwise rotation. So the torques have opposite signs. So if one torque magnitude is epsilon 0 E max squared A squared over D, A squared D over 2, the other torque is in the negative direction, minus epsilon 0 E max squared A squared over 2 multiplied with D over 2. So it's R cross F. So here I note that torque is R cross F. Okay, so this must be equal to moment of inertia times the angular acceleration I alpha, according to Newton's second law, rotational form. So if I write the net torque here, torque is epsilon 0 E max squared A squared D over 4. So how do I obtain this? So I multiply top and bottom with 2. So this is 2 epsilon 0 E max squared A squared D over 4. This is epsilon 0 E max squared A squared D over 4. So I subtract them. I obtain epsilon 0 E max squared A squared D over 4. This is equal to the moment of inertia, which I calculated to be m d squared over 2 multiplied with alpha. Now you can see here, this d will get rid of this square, and then I will have this 2 making this 4, 2 here. So that will give me my final answer for alpha from this equation. Alpha is equal to epsilon 0 permittivity of free space A squared E max squared divided by 2md. So let's check this answer here. Epsilon 0 A squared E max squared divided by 2md is alpha. Now we can substitute the numbers for alpha. Alpha is equal to permittivity of free space 8.85 times 10 to minus 12 farads per meter multiplied by E max A squared 1.5 10 to minus 2 1.5 centimeters squared. The E max is 1.25 newtons per coulomb, so E max squared divided by 2md. So 2, each of them were 4 grams, 4 times 10 to minus 3, and the distance d is 1 meters. So this gives me the final answer for angular acceleration as 3.89 times 10 to minus 13 radians per second square. All right. So in this problem, we have an extremely light rod here, so that has no contribution to the moment of inertia or it has any weight. So we consider this inside vacuum, so there is no friction of any sort with the surrounding material, and there is no friction with this axis of rotation. So when we shine light on these two surfaces, one is completely absorbing, one is completely reflecting, the electromagnetic wave is approaching this from the same side. The torque due to this pressure being exerted on this side is in opposite direction to the torque being exerted on this side. And the torque is equal to R cross F. So using the right hand, we follow the position vector of the point of application of the force with respect to the pivot point here, and we take the cross product with the force, so that gives us a torque vector into the page here. Here we obtain R cross F. The torque vector is out of the page, implying that this is clockwise rotation, this is counterclockwise rotation. Okay, now we need to know the moment of inertia of this setup. We're given that these are point masses, so it is md square over 4, md square over 4, sum over I, ri square mi. That's the moment of inertia. So this gives us md squared over 2 for the moment of inertia. Now, the pressure that is being exerted on these two surfaces is the average intensity I divided by C if it's complete absorption. It's twice I average over C if it's full reflection, because the change in momentum in this case is twice that of the complete absorption case. And we calculate the average intensity as the average value of the magnitude of the pointing vector, and E is equal to BC from Maxwell's equation, so we can use this result. And we can calculate the torque R cross F d over 2 times one force and minus d over 2 times the other force. One is for complete, this is for full reflection, this is for complete absorption. The net torque is equal to I alpha, that is Newton's second law rotational form, right? So we are writing sum of all the torques in the system, sum over all the torques is equal to moment of inertia times alpha. That is the net torque acting on the system is moment of inertia times the angular acceleration. That's Newton's second law rotational form. So from this equation we obtain alpha. Md squared over 2 alpha is the net torque, and we can calculate alpha here, and when we substitute the numbers we obtain a relatively small angular acceleration, 3.89 10 to minus 13 radians per second square.